Student, I am Dr. Ajay Kumar Sinha. Last class I have discussed isothermal and free expansion of an ideal gas, and I have told you 5-6 relation. Last 3 relation what I have discussed, that is equal to Q is equal to minus W, and minus W is equal to P means pressure into volume change, that is the V final minus V initial. This is the first last 3 relation. In that first one is Q is equal to minus W, and minus W is equal to pressure into change in volume, that is a final volume minus initial volume. Second relation I have discussed, that is for isothermal reversible change. The first one relation what I told you, that was for isothermal irreversible change. For isothermal irreversible change I told you Q is equal to minus W, and minus W is equal to P into change in volume. Now I am going to second relation also I discussed for isothermal reversible change, that is equal to Q is equal to minus W, and minus W is equal to, because it is reversible, that's why work done minus W is equal to, that is A N R T ln V final divided by V initial. Okay, that I discussed. And third relation I discussed for adiabatic change, means when Q is equal to 0, then in that situation delta U means change in internal energy is equal to W adiabatic, WAD, a small ad you are writing with W. Then these last three relation I have discussed. And also yesterday I discussed that delta U is equal to Q minus P into change in volume. Delta U is equal to Q minus pressure into change in volume. And one more relation I have discussed, that delta U is equal to QV. Q is here heat at constant volume. Then total 5 relation yesterday I have discussed, and all relations are important. Okay, minor changes there, all are important relation. Now I am going to discuss new term, that is the enthalpy. Enthalpy, it is denoted by H, capital H, enthalpy. This is also actually a state function. Enthalpy, what is the enthalpy? The enthalpy is also a state function. Then what does it means? Enthalpy is a new term you should understand. Okay, now understand. Heat absorbed at constant volume, I have told you. Heat absorbed at constant volume, that is the QV. I told you delta is equal to QV. Means heat at constant volume. I have already told. That is equal to change in internal energy, means delta is equal to QV. But now what we are going to do, that is at constant pressure. But most of chemical reaction are carried out not at constant volume, but in test tube under constant atmospheric pressure. Then we need to define another state function which may be suitable under these conditions. When pressure is constant, that time what will be the new term, means internal energy, what will be the internal energy, okay, that also we are going to make it link with delta U, and delta U means internal energy, change in internal energy, how it has a link with you can say heat at constant pressure. Heat at constant pressure. You have seen heat at constant volume. Now heat at constant pressure. That you have to understand. Then we know that delta is equal to Q. Delta is equal to QP minus P into delta V. When pressure you are considering constant pressure, that time heat content will be QP. Then now this delta U means change in internal energy, you can write QP, a small p, with Q you write a small p down, minus P into delta V. Okay, that nothing like that. First law of thermodynamics, then same equation is there. Delta, there you were writing delta U is equal to Q plus W. That is thermodynamics, Q plus W. Then here W value you have put minus P into delta V. Now only change is that in the place of Q, now you are writing QP, means heat at constant pressure. That is the only change. Then delta U is equal to QP minus P into delta V at constant pressure, where QP is heat absorbed by the system and minus P delta V represent expansion work done by the system. Okay, this relation already you are knowing. This is the not new. Now what you are going to do, what we are going to do, what I will tell, that is the new things. Here now just we will use, always there is a change. And change in means what? From one position to the other position, the volume is changing, pressure is changing. Then two subscript you can use, one for the initial and two for the final. Only then final minus initial, that is the change, delta you are using. Then only these things we are going to use now. Then delta U you are writing. Then when delta U you are writing, then how did delta U came? Then it means U1 was there initial and U2 was final. Then final minus initial means U2 minus U1, that is the delta U. Hence in the place of delta U, you are writing U2 minus U1, and then that is the delta U. And after that same what first law of thermodynamics you have written, same thing now you are writing delta U2 minus U1, that is equal to now QP minus P. Again volume change is there. There you were writing P into delta V. Then in the place of delta V again you can write V2 minus V1, means final minus initial. Final volume minus initial volume. Then you can write here like V2 minus V1, means U2 minus U1, that is equal to QP minus P inside bracket. In the place of delta V, you write V2 minus V1. That's enough. That's enough. And after that, you just do rearrangement. U2 minus U1 equal to QP minus P into V2 minus V1. Then both second 2, 1 and 2 are script enough. You have subscript first and second you have written. Then both we can say 1 script bring together and 2 script bring together. Okay, means after the rearrangement you will get QP is equal to means 2 script 2 write together, and script 1 write together. Then you will get QP is equal to U2 plus P into V2. P into V2. P is a constant. Okay. Then QP is equal to U2 plus P into V2 in one bracket. In other bracket you can write U1 plus P into V1. You have not done, only simply rearrangement you have done, nothing new. Okay, only rearrangement you have done. Then you will get already this QP was there, then that QP is equal to what that you have done. Then for that both one script you have written in one bracket, two script you have written in another bracket. In between the two bracket minus, automatically minus sign will come. Then now here you are going to create a new term, means U2 plus P into V2. U2 plus P into V2 means for U and PV. In general way I am telling you are going to use a new term, that is the H. That is called enthalpy. Enthalpy is equal to what? Then internal energy plus work done. Internal energy plus work done means here you are writing U2 plus PV2. That's why you will write H2. H2 you will write. Okay. And for U1 plus PV1 you will write H1. H1 means H2 minus H1. Simple way, U plus PV, that is called enthalpy. H is equal to U plus PV. Don't forget, this is the new things. This is the new things. H is equal to what? Then U plus PV. U plus PV. H is equal to U plus PV. Don't forget. H is equal to enthalpy. Then now you can write only on this basis that QV is equal to H2 minus H1. H in the first bracket U2 plus PV2 was there. For that you have written H2, means final enthalpy, minus initial enthalpy means U1 plus PV1 means H1. Then now you got new relation, that is the QP. QP is equal to delta H. H2 minus H1, that is called delta H. This is the new relation. Just like UV delta U is equal to QV, delta H is equal to QV. Last class I have told you. Now today you got QP. QP is equal to delta H. Last class I discussed QV is equal to delta U. Now QP, pressure, QP at constant pressure, that is equal to delta H. And delta H means always you can think H2 minus H1. Like other terms, delta P means P2 minus P1. Delta V, V2 minus V1. This is understood. Hence here you can write QP is equal to delta H. This is the new relation I have told you. Okay. And here one thing again I tell you, if ordinary Q is there, just like in first law of thermodynamics, you have written that you know that U is equal to Q plus work done, Q plus W. Then here Q, it is not written whether it is at constant pressure or constant volume. It is not mentioned. Only Q they have written. It means only Q is there. Then Q is path dependent function. But if it is at constant Q at constant volume or Q at constant pressure, then it is not path dependent, it is independent. It is independent. If it is at constant pressure, at constant volume, Q is at constant pressure or at constant volume, in that situation it is independent of path. It is independent of path. Okay. Then ordinary Q is dependent of path, dependent function, path dependent function. But this at constant pressure and at constant volume, that is not actually path dependent, it is independent. Okay, H is a state function, just like P, B, T is a state function. H is also a state function because it depends on U, P and V, all of which are a state function. Therefore, delta H is independent of path. How you have made change? It does not matter, like P, V and T. Hence, QP is also independent of path. Okay, this is an important thing. 1 mark question is asked in many examinations. For finite change at constant pressure, if suppose pressure is constant and some change is going on, then delta H is equal to delta U plus delta PV. Okay, this again is another relation I am telling you. Delta H is equal to delta U plus delta PV. But because pressure is constant, then if change is going on, it means change is going on only in volume. That's why you can write, same things you can write into P into delta V. Now you have written delta PV, but P is constant. Hence you can write P into delta V. Because volume has changed. When pressure is constant, volume can change. You know all the things. Now atmospheric pressure. Now see, pressure is constant. Then you can do any change in volume by heating it. That's why delta H, already I told you that H is equal to U plus PV. That is the enthalpy. H is equal to U plus PV. Now on that basis, you are writing, if final and initial both you are considering, then in that situation H will become delta H and U will become delta U and PV will become delta PV. But because pressure is constant, you can write P into delta V also. Then this is the relation. When H is changing, U is, when H is changing, H1 to H2 minus, U will change U1 to U1 minus, and V will change V1 to V2 minus. Then change you can write like this: delta H is equal to delta U plus P into delta V. Okay, same basis, H is equal to U plus PV. Same thing is there, only delta you have introduced for the two state. That is the only change. H is equal to U plus PV. Same thing you are writing in the same, just you have introduced delta term. Then delta is equal to delta U plus P into delta V. Okay. Then here again now you can think, if a volume is constant, then what will happen? In this relation, delta H is equal to delta U plus P into delta V. If volume change is 0, then what will happen? Means constant, no change in volume. Then this term P into delta V term will become 0. Because no change, delta V is equal to 0. Means constant. Then no change. Hence in this equation P into delta V will be equal to 0. Then what will remain? Only delta H is equal to delta U. Only this will remain. Then this is the, you can say, whatever will be there, U plus PV, you know that U plus, because volume will not change, it will be as it is. Then delta U plus P into delta V, you can tell W also, P into delta V. Then whatever work was there, that will be only that work. then just like U plus W, this delta U plus delta V. Then here V is a constant. It is important to note that when heat is absorbed by the system at constant pressure is constant, then we are actually measuring change in the enthalpy. When we are supplying the heat, then it means we are measuring the enthalpy. Okay, when heat is absorbed by the system at constant pressure is constant, heat is supplying, it means we are actually measuring change in the enthalpy, and we know that, and hence actually we know that delta H is equal to Q, delta H is equal to QP. Already I have told delta H is equal to QP. Hence, if you will put, you can say this delta in the place of delta H, you can write the QV also. Then you will get again new relation, that is the QV is equal to delta U plus P into delta V. Okay. Then now here you should understand, when delta H is equal to QV means heat absorbed by the system at constant pressure. Heat absorbed by the system at constant pressure. Then now again you can know delta H is equal to Q. Then sign of Q I am talking about now. What will be the sign? Then delta H may be negative, delta H may be positive. Then when heat is going out from the system, if heat is going outside, then it is called exothermic reaction. And when heat is going to be absorbed, then delta H will be positive. Delta H will be positive. These things you remember always. Delta H is negative for exothermic reaction, which evolve heat during the reaction, and delta H is positive for endothermic reaction, which absorb heats from the surroundings. Okay. Now here delta H actually at constant volume. At constant volume means what? Delta V is equal to 0. And then what will happen here? Delta V is equal to 0 and delta U is equal to QV. How? Then relation you know that first law of thermodynamics, according to that, delta, already I told you that delta H is equal to delta U. Delta H is equal to delta U plus P into delta V. P into delta V. Then here, what you have understood? That in this relation, delta H is equal to delta U plus P into delta V, and delta V is equal to 0. Then delta, it means it is 0, then delta H is equal to delta U. Delta H is equal to delta U. From the relation, delta H is equal to delta U plus P into delta V, and delta V is 0, suppose. Then P into delta V becomes 0. Then delta H is equal to delta U, and delta is equal to, already told you, QV, heat absorbed at constant volume. It means what? That delta H is equal to delta U, that is equal to QV. Okay. Then this is the again a very, very important relation. Means all are the smallest one. You already knowing, only just you have to link, make it, you should make it link. Then how delta and delta H is there? Then delta H and delta U both are same, and that is equal to QV. All three are same things. Now again you know that here delta H is equal to delta U plus P into delta V. Now suppose change is going on. Delta V is suppose not 0. Pressure is constant, but volume is not, you can say, constant. Then in that situation, if change is going on, then final minus initial will be there. Hence, when final minus initial will be there, then also you know from ideal gas equation PV is equal to nRT. PV is equal to nRT. Then by using this relation, you can get for the initial and final volume. When pressure is changing and pressure is constant and volume is changing. When pressure is constant and volume is changing, and you are applying ideal gas equation, then what will happen? PV1 is equal to N1 RT and PV2 is equal to N2 RT. Correct? Which is changing? For that you have written 1 and 2. Okay, for the initial 1. Then PV1 that is equal to N1 RT. And for the final state means PV2 that is equal to N2 RT. Then now this you can write both final minus initial. Final minus initial, then what will happen? PV2 minus PV1. Then P is a common, you can keep it out. Then you can write P outside, then V2 minus V1. Same way nRT is there on that side. Then N2 minus N1, RT is common, you can write outside. Then N2 minus N1 means you can write PV2 P inside V2 minus V1 that is equal to N2 minus N1 outside RT. Then V2 minus V1 you can write delta V means P into delta V, that is again same way N2 minus N1 delta N you can write. N is the number of moles, you know, in the beginning and after the reaction means a reactant and product. In the beginning means reactant and product means initial state is reactant and final state is product. Then you can write for the difference N2 minus N1 that is for delta N. You can write delta N RT. Hence you can write P into delta V is equal to delta N RT. Then here in the equation what we have derived, delta H is equal to delta U plus P into delta V. Then here P into delta V for this P into delta V, now we got P into delta V is equal to nRT. Then here you can put in the same equation. Then you will get the relation delta H is equal to delta U plus delta nRT. Delta nRT. You are not doing anything. Very simple things. Only you are just putting the value. P into delta V is equal to nRT, delta nRT. For the reactant and product minus reactant means final state minus initial state. Then that delta P into delta V value now we have written. Then now a new relation you got, delta H is equal to delta U plus delta N RT. This relation is used in solving the numericals. Okay, then I have discussed relation. We have derived relation also with delta H and delta U, and also relation between delta H, delta U and PV, P into delta V, and also P into delta V is equal to delta N RT. A simple relation is there. Then now you got new relation, that is delta is equal to delta U plus delta N RT. Now I am going to, in the end, I am going to solve one numericals. Then it will go in your mind, and how it is use the formula, this relation, that you will understand. Okay. Then numericals, question I am reading you. If water vapor is assumed to be a perfect gas, just you have to consider. If water vapor is assumed to be a perfect gas, molar enthalpy change means delta H. Molar enthalpy change for vaporization of 1 mole at 1 var and 100 degrees centigrade is 41 kilojoule per mole. Calculate the internal energy change when two conditions are there. First condition, when 1 mole of water is vaporized at 1 var pressure and 100 degree centigrade. And second, 1 mole of water is converted into ice. Question is long, but you should not fear. These are very easy. Again, I am reading the question. I am explaining. If water vapor is assumed to be a perfect gas, generally it will be volume. Okay, you consider perfect gas. Molar enthalpy change means delta H value is given, that is a 41 kilojoule per mole, and they have given these things. Molar enthalpy change for vaporization of 1 mole of water. 1 mole of water means delta N is equal to 1. Okay, delta N is equal to 1. 1 mole of water at 1 var means pressure is 1 var and temperature is 100 degrees centigrade. Then calculate the internal energy U. You have to calculate internal energy means delta U. You have to calculate when 1 mole of water is vaporized. 1 mole of water is vaporized means liquid is there. Now it can going to be gas, vapor. Then water is vaporized at 1 var and at 100 degrees centigrade. Generally water will boil at 100 degrees centigrade. Then okay, then it means H2O liquid is going to convert into volume. H2O gas. H2O liquid is going to convert into H2O gas. Then here delta H formula, what I have derived, that formula you are going to use. Delta H is equal to delta U plus delta N RT. Then here delta H value is given. Delta H value is given. Delta N value is given. R value is known. Temperature is also given. Then what is the problem? Delta U is equal to delta H minus delta N RT. Then here delta U you have to calculate. Then delta H value they have given in question. Delta N value is also 1 mole given. R value you are knowing. T temperature is given 100 degree. You can convert in Kelvin. Then 273 plus 100, 373 Kelvin. Then all values given. Then you put the value and you can get the result. Means delta U is equal to U. Delta U you are calculating. Then delta U is equal to delta H. That delta H value 41 kilojoule per mole. It is given. Minus delta N. Then delta N is equal to 1. R is equal to 8.31 joule per mole per Kelvin, and temperature is 100 degree centigrade means 273 plus 100 373 K. After the solving all the things, you will get the answer 37.904 kilojoule per mole. Means delta U you will get 37.904 kilojoule per mole. Then first is over. Second part, what was there? Second part, that 1 mole of water is converted to ice. Then means now water is converting, means liquid is converting to solid. Liquid is converting to solid. H2O, liquid is converting to H2O solid. Then here volume change will be negligible. Delta V will be negligible. No change in there in volume. Okay, minute, very negligible change will be there in this when they are converting, liquid is converting into the solid ice. That time volume change will be very less. Then now in this situation, because volume change is 0, volume change is 0, means P into delta V is equal to delta N RT. Then that will be 0 because volume change is 0. Then delta N RT will be also 0 because P into delta V is equal to delta N RT and volume is 0. Then P into 0, 0. Then N delta N RT is equal to also 0. Then in the above equation, means delta U is equal to delta H minus delta N RT. Then here delta N RT will be 0. Then delta U is equal to delta H, means both are equal. That is the delta H value is given 41 in question, 41 kilojoule. That is that will be the equal to change in internal energy. Part 2 means when liquid water will convert to ice, that time change in enthalpy will be equal to change in internal energy. Okay, both will be the same. Then delta H value is given in question. It means 41 kilojoule. Both are same. Both have same unit because both are energy only. H is also energy and U is also energy. H is equal to, always keep in mind, E plus W means work done. Then E is internal energy. Internal energy U also you can write, E also you can write, no problem. Then H is equal to U plus W, that U is energy and W is also heat energy. Both are energy. That's why units are same. Hence in this question delta U is equal to 41 because delta H value already given in question. Then delta U is equal to delta H, that is equal to 41 kilojoule per mole. Today I am stopping only here and next class again we will meet. Thank you.